Hello everyone, and welcome to my talk on FTG in the mining cycle, where, how and why use FTG in your exploration programs. I'm Colm Murphy, Chief Geoscientist with Bell Geospace. Today's talk will cover the role of FTG in what is now generally coming to be believed to be at the beginning of a new mining cycle. Such a cycle is likely to be both exciting and challenging as we explore and exploit new reserves of metals needed to get our economies back on track in a post-pandemic world. Exploration, of course, is the bedrock of our endeavours, and FTG has a primary role to play in terms of not only identifying target geology, but also with upscaling our understanding of the geological complexity that hosts these targets. I will describe this role from FTG, and we will see examples of geological sensitivity from surveys around the world where gravity signal is required for detection. FTG allows us to build what we call as a full spectrum or broadband gravity data type. The technology measures the rate of change of gravity in all directions of the field as presented by the subsurface geological density contrasts. And these multi-measurements of the field, that is the measured components, they're processed simultaneously and output a stable, high signal to noise tensor and a conventional gravity field product. And the key strength of the FTG is a clear ability to identify density changes, structural shapes, and contact information directly from the data in what is considered as the highest resolution gravity product on offer to the industry. The schematic diagram helps us to visualize what is retrieved. The lower panels show 3 geological models and the upper panels their FTG response. The black and the red curves are picking up on the gravity and the TZZ, and we can see from a low density response to a high density response and then a density contrast. That's quite clear. The curvature anomaly pattern, this is retrieved measuring the curvature of the field, retrieved from XX, XY and YY when you combine them. And they directly relate to curvature as shown by geology, be it a diatreme, a low density diatreme structure or a positive diorite dike. And even in here we see an estimate of it with the changeover in density from the granite to the sedimentary basement. The gradient then is fantastic at mapping edges of these same structures, but more interestingly, it does map directly contacts as shown by clear positive anomalous responses associated with that fault. And we use these 3 primary elements in our interpretation workflows. And we can generally surmise it for exploration with FTG as coming to 3 primary applications. The TZZ and the gravity will allow us to identify lithologic change, that is a density change exhibited by going from felsic to mafic rocks, sediment against igneous and basement. Then the structural shapes, these manifest themselves as domes or folds or ridges, channels, craters, cones, plutons and many more. They all show density contrast and formulating 3-dimensional shaped features, and we can directly relate them to where we are in the geological exploration model to identify mafic, ultramafic intrusives, granites and weathered zones and the like. And then the contact edges, they allow us to pick out faults, unconformities, contact zones, and we can relate them to dikes or alteration zones and the contact aureoles themselves. So where has FTG been used? FTG has been used all over the world, wherever a gravity signal is required. And none more so as shown on the map. At Bell Geospace, we've been acquiring FTG for over 25 years on many a survey, 500 plus at this stage, in 50 countries. We own 4 instruments and 3 aircraft, and we measure and record the FTG, conventional gravity, magnetics, and LiDAR. The white dots are representative of where we've been most proactive and in many parts of the world. The first example I'd like to show you, this is a copper porphyry target, and the image on the left is a TZZ response showing a very positive anomalous response indicating high density. It is then when you analyze the tensor component information, we can sieve through that anomalous response and identify 11 clear targets. The next example is from South America in Uruguay. As a gold exploration program and a project with Eurosur Mining. The Lascano area is quite interesting structurally. It's a basin that had developed associated with the opening of the South Atlantic, and you had intrusion of a lot of igneous and mafic intrusive dikes and tholeiitic basalts being extruded as well. Here we see the positive gravity response associated with such a ring dike feature with an intrusive in the middle. When we look at the tensor information, and this is a singular image representative of the full tensor, all of the components are combined. Where we have positive structures, positive density, and a positive gradient, we get these blended colors of the whites and yellows, pulling out the beautiful shape of the associated with the ring structure. We even get the hint of a second one out here to the west. And then we see an additional intrusive structure in the center. The next example is from Eastern Africa. It was a copper and nickel exploration exercise. It was a project over an interesting geological area. We see a very large positive linear gravity feature, and we see two additional ones out here to the east. This is the corresponding magnetic data, and we see the thin linear expression associated with the dikes, but we don't get any magnetic response associated with the positive gravity structure, and as a result, we don't really see these two targets out here. This is fantastic because the gravity from the FTG has helped us, together with the magnetics, to be able to build a detailed geological framework map when we want to pursue and follow through with detailed exploration. The next example is from the Kiruna region in northern Sweden. This is the iron ore exploration project. It's in an iron ore enriched area. What we see are positive gravity anomalies associated with IOCG deposits, and this was a relatively new feature of the structure identified quite clearly. Other information are linear transfer faults, which extend further south, and where there's a lot of activity for nickel and cobalt exploration. How do we do FTG? We acquire data on a Basler BT-67. We own 3 of these, and some of you may recognize this aircraft as the DC-3, and you would be right. It's a reconditioned and upgraded version of the DC-3. It's got modern avionics, it's got twin engines, and it's got long-range fuel tanks, meaning that we've got fantastic productivity. The benefit of having the very long wingspan means that we can fly low and slow and maintain incredible stability while it's in acquisition mode, returning with some fantastic high-quality data. So why would we do FTG in an exploration, especially going forward with the new challenges that we're all facing? It's generally believed that, yes, we are in a new mining cycle, and with that, it's the energy transition and need for more metals. And we need to rethink our exploration strategies in both the brown and greenfield setting. There's numerous data sets out there, and geology is very well known, but we need to ask ourselves, is this the right geology that we need to know about? Do we have the right technology? Do we have sufficient data? And of the data that we have, is it of the right quality? In other words, do we need more? We know that from many an exploration project out there, that you'll have the EMs and the magnetics, and they will see a lot of the shallow targets and give you a lot of detailed, clear depiction of that geology. But sometimes, and as you go in to find more targets in the same areas, the requirement is to go deeper, to look in more subtle areas, and sometimes these techniques may not be sufficient. For FTG, with our long-standing leadership in deploying the technology all over the world this past 25 plus years, we come to respect and observe its primary application. One of them is that we can go from province to district to prospect scale resolution with the FTG. It allows you to bridge the gap that often exists between a regional ground gravity network and the required gravity detail over prospect scale. In addition to that, we can clearly define density changes, identify structures and map contact edges in a data set and relate them directly to geology and to build the important geological framework maps. So the case history that I want to take you through, that we can explore some of these concepts, is from a survey that we did in New Brunswick. It was over the Bathurst Mightycap. The Bathurst Mightycap is one of the oldest mining districts in Canada. There are 46 known VMS deposits and as many again known occurrences. Zinc, lead and silver are the primary metals that have been produced, but there's also copper and gold deposits there. Most of the discoveries have been made in the 1950s, and mostly have been found at the surface or below thin and a discontinuous glacial sedimentary layer. So much of the knowledge that we have in the geology comes from that surface mapping, but also from the many airborne geophysical surveys that have been conducted in the area. The complex tectonic sitting for the area is described as a back arc basin, initiating in mid-Ordovician times and ending with the closure of the Iapetus Ocean. The rifting initially led led to opening of the oceanic crust. And the area is quite complex. For starters, we'll take a pause a minute and have a look at it. The large brownish yellowish colours here are primarily associated with felsic volcanics, and out here we got a basaltic, tholeiitic basalt coverage, and most of the VMS deposits are either in along here in the Tete Gouche or in the California Lake formations. Up along in here we have a series of blue schist facies thrust sequences, and it's with the closure of the Iapetus that a lot of these individual blocks were amalgamated and squished and slid past each other to create a complicated tectonic map. But realistically, a lot of the deposits have been found, have been found, but there's a lot of information yet to be retrieved from this and to add to this geological framework map. When this was, New Brunswick was a primary producer of zinc and lead in its day, and then back in the early 2000s, it's generally considered that they needed to find more in order to prolong the life of the mines and activity in the area. As part of that exercise, Noranda Exploration, with the government in New Brunswick, commissioned an FTG survey at 15,500 line kilometers of 200 meter line spacings. This is the survey polygon that we acquired. In looking at some of the existing geophysical data for the area, this was the magnetics on the left and the EM on the right. And you can see it's a wonderful display of anomalous patterns. A lot of the high frequency, high amplitude responses are indeed associated with the surface and very near surface geology. We see the basalt pattern coming through in the magnetics. We see some wonderful structures and magnetized ultramafic rocks and the like. And then with the EM, we're getting an indication of the conductivity on some of these rocks themselves. You'll also see that a lot of the geological interpretation is actually drawn from these two data sets, plus, of course, with the assistance and constraining information from the many boreholes that have been drilled. These two data sets have been quite instrumental in helping with the discovery and development of the Camelback deposit. Of course, the object of the exercise was to see if we can use these data sets if they can go deeper, and that's kind of challenging because there would have been a lot of it. There's a conductive layer, so the technologies themselves might have been largely sensitive to that surface and near surface, and not necessarily being able to pick up on the deeper geology or the more subtle geology in the area. The ground gravity data that was made available was acquired by largely, was held by the NRCan in their geoscience data repository. The data is a ground survey over many years, acquired over many years, large, typically about a 600 meter station spacing, even though in part it can be 1 or 2 kilometer station spacing. And the anomaly pattern that you can see here, less sensitive to the surface and near surface geology, but certainly picking up on the deeper. Where we have the higher amplitude warm responses, that is there are blue schist facies rocks up here, but there's not as many ground stations up here, so we're tend to missing some of the record. We see the presence of the basalt sequence here in the synformal structure, and we get a hint of the antiformal structure that's with the wrapped around sediment. But out here to the west and to the south somewhat, it's less clear. There is less sensitivity to the geology of interest in many ways. The gravity field retrieved from the FTG shows a lot more character. There is an increased sensitivity. For starters, we do see a lot of the same features in here that we see with the ground data, and that's encouraging, and that helps to support and confirm the validity of the FTG. But we also see some more detailed, and I suppose that's not too surprising with a 200 meter line spacing over all of the area. For example, up in here, we're getting clear depiction of the blue schist facies thrust sequences. We're also picking out some linear fault framework or contact information out here in the western extent, where we don't really see that in the ground data. The advantage, of course, in having the FTG is that it allows you to get ground gravity resolution over areas where it's difficult just to acquire ground gravity. And these could be over swampland or areas of heavy vegetation or difficult terrain. If we look at a difference map between the FTG and the ground gravity as shown on the right, we can see the step up in value from the FTG. The warm colors are picking up on additional geological information. The green colors tells us that there's no real difference with the ground gravity. The warm colors are clearly picking up on some new information that we had not really been able to detect previously. We get a very sharp definition of this feature down here. And it's wonderful in the sense definitely with the sediments as they wrap around this antiformal structure. Of course, there are key different ways of working with the FDG, and we've developed an intricate workflow over the years. I wanted to share one of those maps with you right now. And this is what we call is a curvature map. And it is what we call, in fact, the K most positive from the curvature expression. And it really pulls out those anomalous patterns that are most positive, and we can relate them directly to geology. The responses, you can see, they're different in shape and form. There's some very high amplitude, there's some of lower amplitude. A lot of the higher amplitude features are associated with some of the known deposits in the heat steel area, Murray Brook and Caribou, and others are rather interesting. One means, of course, to be able to assess the impact of these anomalies is to bring in the drill hole database and see where the drilling activity has been happening there over the years. And what draws my eye is that perhaps some of these potential targets have been missed. For example, here in heat steel, but also in this particular target zone, somewhere between the Murray Brook and the Caribou, along that fold sequence here as it's expressed in the data. Another mechanism of working with the data is to think about structural zonation and how can we group these anomalies and think about the geological character that's being presented. We do this quite neatly. We identify the first one and we look for lookalike anomalous patterns, and we look for offsets where some of these linear patterns terminate and don't appear to continue again onto any other linear trend. We group the first set here in the heat steel general area, and not only internally, we also see how these form a linear but then just stop short, and we might identify a fault pattern, and so we can start building and adding to the geological workflow or the geological makeup of the area. Another one's out to the west on the Half Mile Lake, and again up in the Devil's Elbow area, and we looked at what separates them as a near east-west trend, and even when we look at Half Mile, they appear to be sitting on the edges of some of these kind of east-west orientated features, and the same for Devil's Elbow. The next one, of course, is over here that groups the Brunswick and the Headway areas, and a lot of the geology here is under the basalt cover, so it's difficult enough to get a clear depiction of the geophysics associated with Brunswick, but yet with the FDG we're getting the hint of it here, perhaps at depth. And then again in here in the centre and up in the north where we have the lesser dense, but yet a clear depiction of the structural trends. And of course, one means to help us as a sanity check is to bring in the geological information that we know about into this map and see can we modify and tweak and change our interpretations and move it all forward. And we got as far as that, and I'd love to be able to share some more of the work, but and it is ongoing. And in fact, we're hoping and we're very excited to see this continue on a work program this year through a collaboration with Doctors Alex Peace and Jeremy Raimondo from the McMaster University, where they will take this information, the FDG with the EM, the mag data, and perform a structural analysis through an intricate inversion exercise on the geophysics to help identify and put the technologies into perspective to help with mapping and learning about the new geology in the area. So it means that summarizing the conclusions, we returned to that slide I had a while ago. We talked about a new mining cycle and the need to rethink exploration. And it is important to think about what we're doing and asking ourselves the right questions. Do we have the right technology? Do we have enough information to help to really define the geological play models that allow us to be more efficient in our exploration? And of course, and that's where we think the FDG kicks in, that it can bridge that gap in going from regional to prospect scale and allow you to map the geology in clear detail. And for when it comes to the BMC, I do think that yes, it can indeed show a connection and allow you to bridge that gap and identify the geology not readily seen with the magnetics or the EM somewhat, but adding it to and reinforce those interpretations. And that it does indeed show an ability to identify a good, clear geological framework map and to complete the exercise and identify the potential for new targets. So that's the end of the presentation, and I thank you for your time today.